Good day to all the participants. I am Bryan or Fabian, along with my co-authors, Jerson S. Sumalinog, Joan S. Vicente, and Engineer Joan, Katherine, and Romasanta from the NU Das Marinas National University, Philippines. Today I am going to present to you our paper entitled GreenSight IoT-Based Greenhouse Monitoring System for the 14th IEEE Symposium on Computer Applications and Industrial Electronics 2024 with the paper ID 147. So for the topic outline, first we have the introduction, related studies, methods, results, discussion, and conclusion, which I will elaborate more later on. As an introduction, greenhouse agriculture has emerged as a vital solution to global food security challenges, witnessing rapid expansion within the agriculture industry. A greenhouse serves as a closed structure safeguarding crops from adverse weather conditions such as wind, hail, and UV radiation, along with temperature and humidity fluctuations. Additionally, it acts as a barrier against pests and insects. By 2019, global greenhouse cultivation has reached approximately 496,800 hectares, driven by the rising food demand and climate change impacts. This growth highlights the pressing need for greenhouse infrastructures, especially in tropical areas where climate change effects are severe. The Philippines has seen the rise of large greenhouse complexes, capable of annually cultivating over 2 million plants, showcasing the country's dedication to modernizing agriculture and ensuring food security. The rapid growth of IoT technology is transforming industries, including agriculture. GreenSight, an IoT-based automated greenhouse monitoring system, aims to enhance efficiency. It integrates components like the Node MCU ESP8266 microcontroller and the HT22 sensor for environmental tracking and tailored actuators. The user-friendly Android app enables remote management. Furthermore, this study highlights the IoT benefits for automated, eco-friendly farming practices. This study aims to demonstrate the feasibility, benefits, and potential challenges of IoT-based greenhouse management solutions, contributing to the advancement of automated and sustainable greenhouse management practices. Greenhouse farming has transitioned from conventional to advanced sustainable methods. Marcellis, Costa, and Uvlink study highlights these efficient techniques, particularly in regions like the Philippines, where the greenhouse complexes reflect a shift to a more advanced agriculture. The integration of technologies such as AI, IoT, and mobile internet has significantly transformed global agriculture. The introduction of IoT-based smart greenhouses is highlighted as a major breakthrough, providing better management features and the possibility of higher crop yields. Smart greenhouse technology, while beneficial, sees a varied adoption globally. In the Philippines, projects like SGPP and Bukidamara Agri-Farm are pioneering IoT integration in agriculture. However, challenges in broader adoption persist, with factors such as socioeconomic and infrastructure playing a role, as noted by White in the context of South Asia. Recent advancement in greenhouse farming and agricultural technology has seen significant contributions from researchers. Caudalie, Jain, and Caragual developed a smart greenhouse model that automates farming tasks, featuring automatic drip irrigation, nutrient provision informed by soil health, and environmental monitoring through sensors, including a GSM module for remote operations. Similarly, Farouk et al. Showcased the use of IoT for greenhouse task automation, with a focus on mobile applications and integrated systems for efficient environmental management. This development marks a leap forward in precision agriculture. To ensure the optimal growth of certain plants, it is essential to maintain specific temperature and humidity levels. For instance, foliage plants need temperatures between 18 to 24 degrees Celsius and humidity of 50 to 60%. Greenhouse systems are key in regulating these conditions by using actuators like automated fans for cooling, misting systems for humidity, and adjustable roofs or heaters to maintain the desired climate for the plant health. The IoT-based greenhouse monitoring system comprises essential components such as the Node MCU 8266 microcontroller as the power controller, the HT22 sensor for humidity and temperature readings, and actuators in the component control system. The system enables remote configuration via an app. In operation, the microcontroller collects data from the DHT22 sensor and communicates with actuators based on instructions receives from the app via a local IP web server. The two images depicts a scaled-down greenhouse prototype that incorporates a Node MCU ESP8266 microcontroller within a box designed for easy wire management. It is powered by a USB-connected power bank and batteries for the actuators. The system includes a PCB connecting the actuators to the power and control units. The PCB design connects three actuators and controlling them through the GPIO pins of the microcontroller and IRFC44 and MOSFET transistors. The microcontroller manages the servo motor via a digital pin and oversees the power supply to the actuators. The sensor is also connected to the microcontroller to monitor the greenhouse climate accurately. The microcontroller is programmed using the Arduino IDE. It connects to the Wi-Fi network using the specified credentials and controls actuators and sensors through the defined GPIO pins. Moreover, the setup function initializes the system, while the loop function reads the sensor data and processes web server requests. Functions are provided to control actuators and report temperature and humidity, with HTTP responses confirming actions taken. The image details an Android application created with Android Studio that features a user interface with buttons and toggle switches. The app's dashboard screen presents temperature and humidity readings and allow manual control of the greenhouse DC motor fan, misting atomizer, and roof servo motor. It also includes a switch to select either automatic or manual mode for the actuator's operation. Additionally, the app includes a monitoring function that utilizes NP Android chart to plot temperature and humidity trends across various time intervals ranging from an hour to a year, providing a valuable resource for observing seasonal variations and evaluating the effects of climate change on greenhouse conditions. The application also allows users to select preset or manual settings for temperature and humidity control in greenhouses. With presets offer defined thresholds, while manual mode lets users set custom values. For the actuator control logic, establishing predefined logic for actuator control is essential in automatic mode to ensure optimal greenhouse conditions, as depicted in this figure. Misting systems play a crucial role in maintaining balanced humidity levels, vital for plant functions like transpiration. Fan-induced air circulation and evaporative cooling effectively control high-temperature scenarios, with studies highlighting the combined efficacy of ventilation and misting in mitigating heat and low humidity. Properly designed roof fans significantly influence the greenhouse microclimate, regulating temperature and humidity simultaneously. In the evaluation phase, expert feedback is collected to assess the final project's quality using ISO 9126 standards, which cover software and hardware quality attributes. 10 experts review the system using a 4-point Likert scale, with scores ranging from excellent or 4 to poor to 0. The average scores for each quality attribute and the overall average were calculated from these ratings. In conclusion, transitioning to a cloud-based infrastructure from a local IP-based system would streamline data management and accessibility, enhance scalability and real-time data processing, and enable more advanced and sustainable greenhouse management practices, fortifying the system's framework for resilient and efficient operations. We furthermore recommend integrating Google Firebase in order to enable the cloud server functionality and control mechanisms to further enhance the capabilities of GreenSight and to enable more flexibility in the application. And that's all for today's presentation. Thank you for listening.